Hello, good morning. So today we're going to be looking at the graphs of exponential functions. So the way we're going to do that is by first looking in the short run, which you can think of as being interesting points in the plane of how this function behaves. So intercepts, horizontal and vertical intercepts, or general behaviors that we can see when we view them in a window, versus the long run behavior, which is let's see what happens when we take the input values to the extreme large values out towards positive infinity and extreme negative values down towards negative infinity. Then we're going to look at a new way to represent that called limit notation, which is preparation for calculus. Limits are what's called the underpinning for calculus. And then we're going to use these graphs to solve equations. So by the end of this, you should be pretty familiar and comfortable with what an exponential function graph looks like, both for growth and decay, what the different parameters mean, and then how to talk about their short run, meaning kind of viewable behavior, versus the long run behavior, what they do at the extremes. So let's jump in. So for the short run, let's remember what the form of exponential functions are. They're usually a times b to the t, or here I'm introducing this k, which represents the vertical shift. So they're all going to be basically of this form or be able to be written in this form from a different form. So how many times can you say form in 10 seconds? So what each of these parts are, right? Here's my output value or my y value, my input or x value, or t, or whatever it might be. Again, if we're thinking of calculator, that's why I say y and x. It's not always y and x. So my input and my output, and then what are the rest of these things? The rest of these things are called parameters. Okay, so we have the input and output variables, and then parameters are usually constants. They're numbers that dictate the shape of the graph. And right, likewise, it's not just the shape of the graph that they dictate. They're changing the values in a certain way. They define the relationship. However, that will affect the graph. So I don't just mean to point to the graphical perspective, but that's what we're focusing on today. So those parameters are a, b, k. Those are what we call parameters. And so let's unpack what each of these are. So for k, this is what we'd call the vertical shift. This tells us how far up or down we're moving this function. A is usually the initial value, but really we can call this the coefficient, okay? Because if we're shifting this thing, then the initial value is going to be moved as well. And we'll talk about that. And then B, we know, is the growth factor or the decay factor. So these are the three parameters that shape the whole graph, that change the relationship. The input and output by themselves don't really impact it that much, right? Just like with a line, the slope and the y-intercept dictate where that line lives. These three parameters are like the three dials, you can think, that change the form of the exponential function. So I'm going to pull up a graph here in a minute, but these are just important to remember what these dials do. So we'll say, if b is greater than 1, what do we know? If b is greater than 1, this is an exponential growth curve, right? It's going to be accelerating in the direction of growth. If b is between 0 and 1, we know that not equal to, if b is strictly between 0 and 1, we know that this is exponential decay. All right, so here normally it should be doing something like this. With decay, it should be doing something like this. Now, here's the kicker. If A is positive, then this all stays the same, right? If A is negative, the stuff flips, because now we're saying, well, you were increasing in the positive direction, but if A is negative, that means each time this thing's growing, it's being multiplied by, let's say, -2. So it's going to take that output that was increasing and flip it across. And so instead of it growing exponentially like this, it's going to be shooting downwards with the same amount of acceleration. And so the same with decay. If it was decaying in this way, it's really now decaying kind of upward like that. So it's a flip across the y-axis. Did I just say y-axis? Across the x-axis. It's a flip across the x-axis. Right? Everybody sees how this was flipped across that axis. Okay. So this is A's kind of contribution. Its sign changes things. Also, the size of A matters, right? If A is between 0 and 1, it's also going to kind of slow the growth of the curve initially, and it dictates where it wants to sit on the y-axis. But if there's a vertical shift of k, then that's going to move where the y-intercept is, right? So if I have just, let's say this is my a b to the t, and then I add some k, whether k is 5, now what that's saying is that this distance here is k. Okay, so it is literally just take the same graph and move it up. So likewise, if this was the point 0a, my y-intercept, then this point up here is going to be what? 0a plus k. Takes everything and shifts it up by k. So we're going to look at this in a graph setting using Desmos. You can do the same thing using your TI-84, but I encourage you to play around with Desmos too, because there's these sliders that can give us some perspective here. And I blew right past this. We have talked about this before, but it's important to remember, right? The y-intercept or vertical intercept for when it's just of the form a b to the t is p of 0, which is a times b to the 0. Anything to the 0th power is 1, so this is really just a, right? So that makes sense that when p of t equals k plus a b to t, we'll use some actual numbers in a minute. This should be equal to, p of 0 should be equal to k plus a b to the 0, right? And what is b to the 0 again? It's 1, so then p of 0 needs to be equal to k plus a. So this would be my kind of new vertical intercept if it's been shifted. Okay. So this is for the short run. Okay. How does this thing curve? Up, down? Does it decay? Does it grow slowly? What's the value of b? What's the value of k? What's the value of a? That dictates these things. Okay. So let's go ahead and look at a graph with some actual numbers. So when I'm in Desmos, you can type in the expression. Usually it only accepts t or x as inputs. So I wrote p of t equals k plus ab to the t, and then it'll notice that you're using parameters. And so we'll say, do you want to add some sliders for these? I'm going to say yes here because I want to play around with these. And so let's take a look at a function that might be something like this. 4 plus 2 times 3 to the t. So what I can do is see that, all right, here my k value, let me mix it up and make it a little bit more unpredictable. So let's say it's written like this. Okay, so if I were to look at this function and say, well, what are my k, a, and b values? What are my parameters? Well, k is 4 here. So with the red curve, let's say I want to move that up to 4. Let me zoom out a little bit. And matching a and b should also match this curve up to be right on top. So my a value looks like it's 2. So if I scoot this up to 2, you'll see now how we have the same y-intercept of 6, which is 4 plus 2. And then the growth factor has to be the same. Right now it's at 1, that's why it's a flat line, right? Because it has no growth or decay. And so if we move it up to 3, we're going to see, hey, look, it's right on top, right? So we can drop this one out and see if that's the case. And now we can just play with this thing and see what effects each of these parameters has on the graph. So let's stay in the short run here for a moment, then we'll start to look at the long run. So k, if I am to move k up and down, what seems to be happening? It's moving the whole graph up and down. Because why? Because why? It's changing the y value, right? It is literally taking, all right, whatever the output of the exponential piece is, and then I'm going to add 3.2, or I'm going to add 10. And that's going to just take those output values and just simply move them up by 10 if we're looking at the graph. So k is very simple change. It will just move it up and down. And we've seen this with other functions as well. Take the parabola x squared, add 4, it just shifts it up 4, or minus 4, it moves it down 4. Same thing. So what about a? Well, a is interesting because it scales the growth, and if it's positive like we're seeing here, and if it's large, it makes it steeper. It also makes the y-intercept go higher, right, or lower, because it's the initial value for this exponential piece. It's where this is starting off. It's like the starting number, and then this tells you how much to multiply that by each time, right? So this is going to both impact the shape of the curve as well as where it lands on the vertical axis, where it intercepts. And so here we see it's going to be k plus a, which should be 5.3. So if we find that intercept here, it's at 0.5.3, and that will change. Okay, so this is when a is positive. You'll notice something happens when I flip a to become negative. It's now growing in the negative direction. And again, think about it. If my initial value is negative 1.4, and then I keep multiplying that by 3, bing, 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 it's going to be hugely negative. Even if k starts off as a positive number, it's going to accelerate in the negative direction. So the vertical shift really can't compete with this multiplier. So when a is negative, that flips it across the x-axis. It's a mirroring. So 1.5 to negative 1.5, you can see the difference there. So lastly, we have the growth factor. How does this change the curve? Well, let's put things more into exponential growth. Let me change the window here a little bit. Make that a little bit smaller. So by changing b, by shrinking it, what do you think is going to happen before I do it? If I make b less, the multiplier less, how is the output going to be changed? Well, it should be growing less quickly if we're multiplying by a smaller number. So if I shrink b, I'm expecting this to have a less steep rate of change. And so as I do that, I see that that's actually happening. As I lower b, it's kind of like laying the curve down to be not as fast as it was before. It's still going to shoot off to infinity. You go out far enough, it's still going to blast off. But changing b is really what changes the bend or the steepness or the concavity of this curve. Okay, so that's when b is greater than 1, and when b is less than 1, it changes how it's decaying, right? So the closer it is to 0, the sharper the decay, because this means we're only really keeping 20% each time. Whereas here, we're keeping 90% or losing 10% each time. And then what happens when we, let's say we're looking at decay, and we flip A. Now that A is negative, we see, okay, it flips it across the x-axis. So now instead of decaying really quickly, it's kind of shooting up and tending towards what would be 0 normally if k were 0, or whatever k's value is. Okay, so we're kind of blurring a little bit between the long run and the short run there, but we're gonna be explicit about that. So ask yourself right now, what does k do, what does a do, and what does b do? And jot that down in your notebook. K shifts vertically. A is the kind of scale factor, you can call it, and it tells you, its sign tells you if you're going up or going down, right? If you're flipped across the x-axis or not. And B gives you the rate of growth. It tells you how steeply it's going to curve. And so in the practice problems, you'll see a lot of graph comparison. And so I encourage you, I'll link the Desmos calculator I just used, and I'll encourage you to play with that before jumping into those problems to see what effects they're going to have. So, right, having a larger b value than another curve means it's going to be steeper. If they're both greater than 1, 1.5 versus 1.4, that's going to take off a lot quicker. And so you can start to kind of deduce what other effects those things will have when you're comparing the two graphs. So this is all in the short run, right? What's happening around the axes, what's happening in this viewable window for the function. And now let's look quickly at the long run behavior, and then we'll do some examples of solving equations using the graph. So long run behavior. We're asking the question, what, getting my words mixed up, what happens at extreme values of the input to the output? And there's really only two answers that can come from this. The option 1, it tends to or approaches a certain number. I'll tell you right now, a lot of times that number is 0. Sometimes it's not. Sometimes it's a different number like 10 or 15 or 68. So could be 0, could be some number k, but it's going to tend to a number, right? So over the long run, it might be settling on some value. So the example we'll use is a cup of coffee cooling in a room. Over the long run, what's the temperature going to be? Well, it's going to settle at the temperature of the room, right? If that room remains constant temperature. So that's one option for long run behavior or extreme values of the input. Let's let it sit in the cup for days or weeks or even years. But we're even talking about longer term than that. We're talking about the shape of the graph. We're talking about huge values of the input. And then option 2 is what we call it diverges, which means it does not settle on a number. And there's two ways that can happen. One way is that it blasts off to infinity. Trying to use the least amount of math terms as possible, so blasts off is pretty good. Blasts off to infinity, or it might just like oscillate and never settle. So something you might see is a function increasing without bound. Hint, hint, we have seen this. Or it might oscillate, meaning it goes back and forth over time but doesn't ever hit and stay on one value. So this is what we'd say it diverges. It means it doesn't converge. So we're either really looking for one of these two things when we're talking about the long run behavior. Does it settle to one number like a coffee cup, or does it oscillate or blast off to infinity or negative infinity? Okay. So one way you'll see this written is, let's say given a function, and here is the temperature function. Actually, we use h here. The temperature of a coffee cup brought to class, or the coffee inside the cup when brought to class. T minutes after brewing. H is temperature of the coffee. So we could look at the short run behavior, and we will do that after. Let's look at the long run behavior. So what does that mean? At the extremes. So one way you can look at this is we use this notation t approaching infinity and t approaching negative infinity. So you probably know by this point that you can't just plug infinity into your calculator and see what happens. It's more of an idea than it is an actual number, right? It is boundless. So when we say t approaches infinity, we're talking about kind of more casually, huge values of t. And so you can approximate this with maybe going into your table and letting t be 100 and then 1,000 and then 10,000 and seeing what happens. Because this is a notion of approaching. So we're really trying to see, is there some tendency to which it goes to? And this is what we also call the limiting behavior. So does it have a limiting behavior? So as t approaches infinity, does h of t approach some number? So what we do is we can look at the graph, and you'll see in Desmos or your TI-83, it's a decay function, crosses at, what's that? I believe in your example it's actually 93 degrees here. Make sure you change that. So I believe it's 161 is the y-intercept. And then it's decaying over time. And what happens is that since it has a vertical shift, you might notice, of plus 68, that it's going to settle on this number over time. So this is what we call the long run behavior. As t increases to infinity, h of t is approaching 68. There's another name for this called the horizontal asymptote. Which says that as t increases without bound, y becomes this number, right? And so it's a horizontal line. And it tells us that the function is going to tend towards this number over time. Asymptote doesn't mean it can't cross it. You can actually have a horizontal asymptote and cross it. It's different from vertical. So it tells us that it's heading towards this line. If I put y equals 68 into my calculator, which you can do, you'd see that these things will align and converge as t increases. Okay, so to write this a little bit more clearly, you say as t increases to infinity, h of t approaches 68. And we write this a different way in calculus, and we're going to start learning this notation now. This is called limit notation. And limit notation says that 68 is the limit of h of t as t approaches infinity. You might hear these expressions used in science or in mathematics called the limiting behavior or the limiting factor. It means this is a bound, this is where it's heading in the long run. So 68 is the limit of h of t. That's where it's heading toward. So the way that we write this mathematically is we use this notation lim for limit. The limit of h of t. And then in the bottom we say as t approaches infinity. So this is kind of the input space down here. And we're talking about the limit of the output. Or you could even write it as the limit as t approaches infinity and use the formula for h of t, which is 68 plus 93.91 to the t. This is equal to 68. This is how we would say this symbolically. So this is one way to say it. This is kind of informal. An informal way to talk about LRB or long run behavior. We want to start practicing using this limit notation to represent it. So the limit of h of t as t approaches infinity is 68. That's what happens. So which of the two options for long run behavior was this? This was option 1 because it was heading towards one number. And again, I saw this from graphing this. I know this to be true about this function for several reasons, right? Ways to investigate this. One would be graphically. See where a horizontal asymptote might be. So for us, we saw that at 68, but this is obviously going to be kind of tough to be accurate with, especially if you're on a TI-84, based on where your window is. This isn't really ideal. This is more like kind of like a step 1 maybe. Another, probably a better way to go would be to use a table. And what you can do is set up for t and for h of t, you put it into your input outputs, right? And for your x and your y1. And then put in increasing values of t that get huge. And you'll see in your calculator that, this might start off at something like 140, maybe cooling off to 100, and then you'll eventually see it's at 68.5, 68.4, and then it will just eventually level off to 68, and you'll just keep seeing 68s in a row. That's meaning that it's tending towards its limiting at this 68. So this is a good way to go to approximate the long run behavior. If you see that it tends towards a number when values are getting huge, then you know that's the limit. Vice versa too. You can do this, or as t approaches negative infinity, how would you do that? Let t equal negative 10, negative 100, negative 10,000, etc., and see if it comes to some value. So you could look at the graph, you can look at the table, or you could look algebraically. And this is something that's a little bit tougher to do and what we do more in calculus. So essentially, I'll teach you one way to do these algebraically using limits with rational functions, which we haven't talked about yet. But using it for exponential functions, the best way to go is going to be using the table and then maybe backing it up, or using the graph as like an exploratory maneuver, right? Does this thing have a limit? Does this thing have a horizontal asymptote? Let me look and see in the graph if that's reasonable, and then use the table to really get a closer answer. So by doing that, you would come to see that the limit is 68 here. Okay. So we've identified this has long run behavior. This has a horizontal asymptote at 68 as t goes to infinity. But what about when t goes to negative infinity? What happens? So maybe you want to hit pause here and try this yourself and see what's going to happen in the table and in the graph. So I'll assume that you hit pause and now you tried it and we're coming back. So for t values, we can take things like negative 10, negative 100, negative 1,000, and so on. And looking in the calculator, what happens to your outputs? Well, I don't have the exact numbers offhand right now, but they should be getting huge. Huge and off to positive infinity, right? If you looked at the graph, why does that make sense? The graph of this curve was like this, and it leveled off at like 68. But what happens as t approaches negative infinity? There's negative infinity down here. What's happening to the outputs? It's blasting off, right? And so here we see that as t approaches negative infinity, h of t approaches infinity. And so what we say is this diverges to infinity, or that the limit doesn't exist. So if you were asked to state the limit, to find the limit, we'd say this does not exist, or DNE, or in some cases, and sometimes you'll see this, it's kind of frowned upon, but I just want you to be aware of it. People will say that it just equals infinity. Okay? I can see some benefit in that because you're saying, instead of saying it just diverges, we could ask, well, does it oscillate? Does it blow up to negative infinity? Does it go to positive infinity? If you say it equals infinity, then you're giving me some more information. But I'd probably prefer that you say something like this. Now, in the software for answering quick fire questions, it's either going to be one of these two. But on exams and in your work, I want you to kind of be using this language. It's going to be very helpful, especially for those of you who go on and study limits in a little bit more depth. You won't have this misunderstanding that can be harmful to your understanding. So, anywho, here as t approaches negative infinity, h of t approaches infinity. So we say that the limit doesn't exist. So as we go to the left, the limit doesn't exist. As we go to the right, the limit does exist. It's 68, and it has a horizontal asymptote of y equals 68. So there we've got the long run behavior covered. Use a table to kind of see what's happening, and then back it up with the graph. That's what we can do for right now because we can't do it algebraically. All right, so we've got the short run behavior. We know how A, B, and K shape the graph. We see that if you have a vertical shift now with an exponential function, that's likely going to become the horizontal asymptote. Now, whether it's the function's long-run behavior as t increases, or if it's the other way around, right? We see that for exponential growth functions, it would be as t approaches negative infinity, this would approach 68, if that were the function, right? So where this vertical shift affects the long-run behavior depends on the short-run things like A, B, and K. So let's make some kind of general statements here. So for a function that looks like this, what can we say? We know that K is positive, we know B is positive, we know A is positive. Why do I know those things? K has been shifted up. A, the scale factor, or the coefficient, has me still growing upward, and this is exponential growth. So that's how I know all these three things are positive. And so when this is the case, we know that the limit to the left, right, as t approaches negative infinity of p of t is going to be equal to k. And the limit as t goes to infinity of p of t, is that going to exist? Well, this thing shoots off and accelerates to huger and huger numbers, right? So no, this doesn't exist. This actually diverges to infinity. So this is the long run behavior. Here's kind of your short run behavior items. We have the decay function, which we looked at, which means, here's a different function, k plus a times b to the t, where k is greater than 0, a is greater than 0, b is between 1 and 0 since it's decay, right? And so here we see, just like before, the limit as t approaches infinity of p of t. Well, that's as t goes out this way, what happens to my output? It levels off to y equals 68. And the limit as t goes to negative infinity, we know as I take t and go this direction, what's happening to my output? It's blasting off to to positive infinity. So that's the long run behavior here. Now, the two I want you to think about are when I have something like this. Let's draw that a little bit better. Something like this. P of t equals k plus a b to the t. And something like this. K plus a b to the t. First of all, think about what these values must be, and then what the end run behavior must look like. Okay, a good little exercise to kind of stretch your understanding. This is just a simple growth and decay, but if I maybe flip A, change the sign of K, etc., that's going to change things. So what is the long run behavior when that happens? All right, so we've looked at short run behavior, we looked at long run behavior. You know what each of these dials mean, you know what limit notation means. Now let's use one of these things in context to solve an interesting problem. So here we'll work through an example and using the graph to solve an equation. So you might notice that if I have a equation set up like, 150 equals 2 times 3 to the t, and I'm solving for t, solving for the input. The problem is when I go to solve for t, it's in the exponent. There's no algebraic tool I can use to solve for that input. So we're kind of stuck. Anything that you do at this point would be broken. You'd be breaking the order of operations. I will show you that tool later. You might have heard of logarithms. It's the inverse to exponents, but we haven't gotten there yet. So in the meantime, we're going to use this really helpful tool for solving equations graphically. And oftentimes there's times you can't solve things algebraically, so you need to go to a graph. So let's use it. Let's look at this kind of weird example and show you how to solve for the input using graphs. So out in Colorado and Oregon, there's a huge demand for third generation Toyota 4Runners. They're these trucks that last forever. People get them to 500,000 miles. And so their prices have been inflating out in the West more than they have in the East Coast. So it hasn't been 8%. I'm kind of making that number up, but let's use that as a rough guide to say around 2013, their prices started kind of taking off around 8% per year. So let's say I bought a 4Runner in 2013 for $4,500. When will I be able to sell it out there for $7,000? Is it worth it to do that? Probably not. But let's just go through this thought experiment. The price is inflating. When will it hit 7,000 is the question. So again, we can't solve it algebraically. So we're going to need to do something else. So to go to the graph, to solve for input given an output, we use the graph when you can't use algebra. So what we do is we say y1 is the output of our function, which we know is 4,500 times 1.08 to the t. Hey, Melly, how'd you get that? Go back to 4.1 and 4.2 and check it out, right? Here's my a value, my initial value, and then my growth factor b, right? And it's not starting with any vertical shift. We can just model it directly like this. So here's my y1, 4,500 times 1.08 to the t, which in your calculator would be 1.08 to the x, right, in your TI-84. And then in y2, because this is my output 1, and then my output 2 is y2, and we're saying I want to know when it will be equal to 7,000. So I put in the constant value 7,000. And what's going to happen, and I'll show you in an actual graph, is that this is going to map y2 at 7,000 constant. Let's do it like this. And then y1 will be starting somewhere around 4,500 and increase past this level. And that's exactly the point at which I care about. So I'm going to be looking for this t value. So this is kind of step one, is to map these both into your calculator. So let's go ahead and do that. Okay, so we put in our y1 and our y2 here. And then we're going to need to move the window because we're looking at pretty huge values here. So we're going to want to include 7,000 and 4,500. So let's change our xmin and xmax. Hopefully it won't take more than 10 years, but we can adjust that when we get to it. And then ymin and ymax. So I'm going to set my ymin at 0 because we're not going to be talking about negative values. We might even scoot this up. And my ymax I'm going to set at 7,500. And let's see how that does for us. So here's our exponential curve crossing through 4,500 here, and then here's 7,000. So it is right up here. We could shift the window a little bit to get closer, but we've got it in sight. So from there, I'm going to use second calc. This will allow me to find the intersection. So second calc, come down to intersect. It'll ask you first curve, and it'll usually highlight one. You'll say, yep, that's my first curve. Second curve, yes, that's my second one. And then where would you like to guess? And then usually you don't need to worry about this, but I just drag the cursor a little bit closer to the point. It does not have to be that good. And then it will give you your best approximation. So the intersection's at x equals 5.741 and y equals 7,000, right? So what is this saying? This is saying this is where both curves are equal to this value. So that second step was to use, first of all, set the window. Make sure you can see the intersection. Hey, Morty. And then you're going to use second calc, intersect, and then follow the prompts. And then it will give you the spit out of, okay, they're both at the output of 7,000 and the input was at 5.741. And so this is the input value that you're looking for. All right, this is the input that causes this function to reach this value, right? It's where they both agree is at that point. That t value makes them both true. So that's why we're solving for it graphically. They're both taking on 7,000 when t is 5.74. So the question is 5.74 what? 5.74 years until this forerunner will be worth $7,000. And again, I made up the number 7,000, but you can do this with any value that you're interested in. When will it reach this amount, whether it's growth or decay? And you can go in and solve and find the input. So this should be generalizable to a lot of the practice problems you'll be working with. You know about all the dials, A, B, and K. Again, I've got a Desmos calculator linked in the file after this for you to play with to see what I did there. You looked at the long run behavior, what happens with extreme values of the input, how does that affect the output, does it tend towards one number or does it blow up? And then how to use the graph to solve equations. So plugging in two outputs, your formula and where you want it to be, and then finding that place of intersection. Okay, so have fun and I'll see you in the class discussion.